Okay, so hi everybody. So in this video, I just want to provide a quick example of how to approach and solve problems associated with double-slit experiments. So in this particular problem, we have the question, Young's double-slit experiment is one of the classic tests for the wave nature of light. An experiment using red light, lambda is 647 nanometers, the second fringe on either side of the central maximum is 4.9 degrees relative to the central bright fringe. Write an expression for the separation distance but d between the slits. Numerically, what is the distance of d in nanometers? Numerically, at what angle can the first bright fringe be found relative to the m equals 0 central fringe? Answer in degrees. Okay, so let's do this using our standard approach. We're first going to write down what we're looking for. We are looking for d, so that's already given. That's what we want. What do we know? Well, we know what lambda is. We know lambda is 647 nanometers. And we know the angle theta. That's an ugly theta. Let's get rid of that. We know the angle theta is 4.9 degrees. So those are just numbers that we know exist. Well, what relates what we know to what we want? Now, remember, we have a couple of different expressions for this. We have the expression d sine theta equals m lambda. And we also have the expression d sine theta is m plus a half times lambda. So the question is now, which of these expressions should we be using? And also we'll realize we'll need to know what m is. We know we've got lambda, yay. We know we have theta, yay, and we're looking for d. But the one thing we don't have is m, and you might go, because this one's the easier one to write down, it's easy to lock into that. But to know which of these expressions we want to use, we need to read the problem carefully. We're told the second dark fringe on either side of the central maximum. We're talking about a dark fringe. Remember, this is the expression for constructive interference. This is the expression for destructive interference. So the relevant equation is this one, because dark fringes correspond to destructive interference. Okay, so we're using this, but now we have to figure out what m we're talking about. And sometimes it's kind of easier to sometimes draw rather than just say, write it down. So again, we have our two slits, and this produces a pattern on a screen. And we can either show this as, a variable signal strength, or we can try and draw it, and I apologize in advance for how ugly this is going to be. But we always have as a bright central dot, that's the 0th fringe. Then we have the next dot, and then we'll have another bright dot. So this dot and this dot, and they would normally be the same size. Give me a break. So this corresponds to the m equals 0 bright fringe for this expression. This is m equals 1, this is m equals 2, this is m equals -1, this is m equals -2. This happens when m plus a half equals 1/2. So here is where m plus a half is 1/2. And this, so that's the first dark fringe. So let's actually fill that in as dark. This is the second dark fringe. And these are the dark fringes on either side. This is where m plus 1/2 is 1/2, so m is 0. But the first dark fringe happens where m plus a half is 3/2. And similarly, this is where m plus a half is -1/2. This is where m plus a half is equal to -3/2. So the specific fringe we're talking about is this formula in the case where m plus a half is 3/2. Now you might say, oh, that's just m equals 1. Yes, that's a way to approach it. So what do we got? We got d sine theta is equal to 3/2 lambda. But what we want is an expression for d, so we have to divide out by sine theta. That gives us d is 3/2 times lambda divided by sine of theta. That's what the algebraic expression ought to be. So let's try that out and see if it works. So we're going to take 3 divided by 2 times lambda. We'll put a star there. Can we put a star there? No, we can't. Okay, 3/2 times lambda over sine of, ooh, that's an interesting way it filled out, but we can ignore that. So let's try that. Yep, we got the right answer. Yay. Numerically, what's the value of d in nanometers? Well, we can figure that out. Notice this, lambda's already in nanometers. So if we just stick in the numbers, 3 divided by 2 times 747 nanometers over the sine of 4.7, we'll see what we get, or sorry, 4.9, and it's in degrees. We hit submit, we get 11360 nanometers. So let's actually write that down. So what we find for that is d is 11,360 nanometers. So that's, fairly big, but okay, that's reasonable. So now we can ask, the last part of this question, go back so we have everything centered properly. Numerically, at what angle does the first bright fringe be found relevant to the m equals 0 fringe? Answer in degrees. So now we want to know the angle of this first bright fringe. Now we're talking about a bright fringe, which is right here. In this case, and as well for that problem, we're going to want to use this expression because this is the equation for bright fringes. And we're asked for the first bright fringe, which corresponds to m equals 1. So in that case, what we're going to want to use is the expression we're going to want to use this expression. But we should again be clear. What are we looking for now? We're asking for what angle do we see the first bright fringe? So we're being asked for an angle. They call it theta b. So we're looking for the angle, and I'll write it over here on the spreadsheet, theta b. What do we know? Well, we know all of this stuff. We know d, lambda, and theta for the dark fringe. So just to be clear, I'll call that d. Now, how do we approach this? What connects what we know to what we don't know? Well, this expression does that. So we know d sine theta b is m times lambda. We know lambda, good. We know d, which is also good. Do we know m? Yes, because we're told it's the first bright fringe. So the thing we know for this problem is that m is 1. Okay, so we know everything. Yay, we just have to solve. So the way I generally approach these is I first figure out what sine of theta b is. For that, you just divide through. So that's going to be m lambda over d. So theta b is just going to be the arc sine, or the inverse sine, depending on how you learned it, of that ratio. Now, you will notice there is no way to do the arc sine in expert TA because we get what we paid for there. So we'll do that over here. Okay, so first we'll calculate m lambda over d. That's just going to be 1 times 647 divided by 11,360, and just evaluate that. So this is sine theta b. Okay, so now if we want theta b, that is just a sine, arc sine, of this thing. That is very similar to that because that's the nature of sines in radians. So if we want to do theta b in degrees, we need to take this thing and convert from degrees to radians, which means multiplying by 180 and dividing by pi, because there are 360 degrees in 2 pi radians. So that's the standard conversion factor. So what we get is 3.3. Now, I'm going to stick that in, and we're going to see whether that works out. It is correct. Now, that was one way to do it. Another way to do it that almost works. Notice this. For the first thing, we had d sine theta was 3/2 lambda. For this thing, we had d sine beta is just lambda. If we take, so the only difference between these two expressions is in this case we had 3/2. In this case we had m was 1. So if we take 4.9 and divide by 3/2, which is 1.5, we also get 3.3. So we could have just recognized that since this is at 3/2 and this is at 1, this should be 2/3 of the way there, and 2/3 of 4.9 is 3.3. That works because sine theta is very close to theta in these sorts of cases, and it's a kind of useful sanity check. So that's kind of how most of these sorts of problems go. You might have some extra trig in some of the problems you're doing, but hopefully this gives you a sense of some of the things that can trip you up, like whether you're talking about dark fringes or bright fringes and how to figure out what m is relevant. Anyway, thank you for your time and for your attention.